Okay. Continuing on, lesson 3.5. So we did one of these examples yesterday where I couldn't really use that algebraic manipulation of dividing by my largest power of x in my denominator because I didn't have like a polynomial in my denominator. I had an exponential function. So we talked about, well, think about when you actually like plug in infinity for x. Exponential growth is way faster, and e to the power of infinity is going to be even a larger value than just infinity itself to the power of 5. So we have something over a larger that would be 0. All right. This one, I like this problem. Again, I have that same equation. I have that x to the 5th over e to the x. Thank you. But now I'm looking as x approaches negative infinity. So if I were to direct substitute negative infinity to the power of 5, that's going to go off to negative infinity. Okay, but if I have e to the power of negative infinity, I'm like, exponent properties. I could bring e to the negative power up to the numerator, become e to the positive power. So now I don't really have this like battle of is my numerator larger, is my denominator larger, but I see here I have negative infinity to the power of 5, which that's just going to be going off to like negative infinity. E to the power of infinity, that is probably going to be larger, but now we have this setup. It's going off to positive infinity, where I really have like a negative infinity, a negative big value, times a positive big value. It doesn't really matter which one's bigger here now that they're both kind of like in my numerator, so I'm not looking like do I have a larger value up top or up bottom. Once I took care of that negative exponents, I have a negative large times a positive large, and a negative times a positive is a negative large number, negative infinity. Would be that limit. I'm going to look at a couple more kind of like that. So basically this graph, you guys, the left end behavior goes off to negative infinity. So if I were to just quick sketch this, I don't really know what the curve looks like, but I know that the left end behavior goes off to negative infinity. And the right end behavior, there's a horizontal asymptote at 0. And it could cross it, so it could do something like this, right? But I still have a horizontal asymptote for this function at y equals 0. I don't remember if I wrote that for this one or this one, but this one would also have a horizontal asymptote at y equals 0. Even if the left end behavior doesn't approach it, you can still have a horizontal asymptote. Okay. 2 more like that, and then we get into the radical ones. Radical ones get a little bit trickier, but not bad. All right, this time I flipped the numerator and denominator. I have e to the x in the numerator over x to the 5th. So now you're like, oh, I could divide by my largest power, but then you're going to have like e to the x divided by x to the 5th. So really, again, we can just do the direct substitution with infinity here and just look at kind of like what's more powerful when I have this set up, which one's going to grow faster. And again, we just talked about this, that exponential growth, that's actually going to be larger. So that kind of dominates the function here. And this is going to be smaller, so this is just going to go off to infinity. Okay, does that kind of make sense? So when you have that set up, you kind of just have to decide which one's going to dominate. All right, negative infinity. This time, I have e to the negative infinity over negative infinity to the power of 5. So again, negative exponent properties, I could bring that down here. That becomes e to the positive infinity times negative infinity to the power of 5. All right, this is going to be a negative large value at bottom, but I have 1 over that. So what would that one equal? Yeah, you got it. 0. Yep. And I have a horizontal asymptote at y equals 0. So this sketch, This time, and you could do this on your grapher if you needed like conceptual confirmation that this is what's happening. My left-hand behavior is approaching 0. And it could, I mean, it doesn't have to come down here. It could be doing something like this too. And my right-hand behavior as x approaches positive infinity is going off to infinity. Okay. I guess I can leave that. All right, radicals. So first we need to talk about a little algebra that you've seen before, but you maybe haven't been too particular with, and it's going to start to matter when we talk about these limits. Okay. If you've ever, and you can maybe just write this in between here if you want. If you've ever square rooted x squared, you've always been taught, hey, those are like inverse operations. The radical like undoes the radical. That's just the same as x. Okay? And that's true when we don't know what x is. But if we do know what x is, such as x is like a really big number or a positive number, or when x is a negative number, think of this setup. Do you guys agree that we could have a positive number squared or a negative number squared? And these are both the square root of 4, right? But here I'd get out a positive 2, and here I'd get out a negative 2. So if we don't know what x is, it could really be, I mean, we say it's the absolute value of x, so that no matter what x is, it's going to come out positive, okay? But it really could be a positive version of that number that's being squared, or the negative version of that number being squared, okay? So you have to be conscious of that, depending on if you're taking the positive x values or the negative x values, okay? So what I mean by that is when we do that algebraic step of dividing by the largest power and we square root x squared, it might come out to be a positive x, or it might come out to a negative x, okay? So because I have like polynomials on top, now I know I have a radical, I still can do that dividing by the largest power of x, okay? Now technically my largest power of x is x squared, but it's underneath a radical. So what we can do is we can times both, which we're really dividing by, the square root of x squared. That's like your largest power here. Okay, so I'll show you how this algebra works. So we have 3x minus 2. Oops. Don't forget your limit notation. I'm going to divide these all by the square root of x squared. Now here, because the square root's already contained in here, I can just add this in. So I'm really dividing everything by x, but I'm writing it like this because that square root of x squared is underneath my radical here. Okay. So here's what you gotta pay attention to: positive or negative infinity. If x is approaching positive infinity, the square root of x is just gonna be a positive x, okay? Because we're only taking the positive x values. Here, those cancel, so it doesn't really matter. We get 2 plus 1 over x squared. All right, now when we plug in infinity, these cancel now too. I would have 3 minus 2 over large is just 0. 2 over positive large is 0. All over the square root of 2 plus 1 over large would be 0. So you end up getting 3 over the square root of 2. Now here's the weird thing about calculus. We don't rationalize. We just leave it like that. Probably going to make you kind of uncomfortable, huh? I don't know if your textbook actually rationalizes. You can if you want to, but on the AP exam, they don't grade you on, like, your arithmetic, so they don't grade you. Remember how I told you that one time, like, you can leave your answer like this? Something like that. They don't grade you on arithmetic, like adding, subtracting, rationalizing. They grade you on the calculus part, so, like, you could stop here. Okay. So let's take a look at the exact same example, but now as x approaches negative infinity. So I'm just going to copy over this step because we would do the exact same thing as here. We would divide by the largest power in the denominator, which the largest power is the square root of x squared. And we'd still get to here. By the square root of x squared. That one already has the square root, so you can just write it underneath the radical. All right. So now we know we're looking as x approaches negative infinity, or another way to think of that is you're kind of looking at, like, all the negative values of x. So this time, when I square root x squared, I'm going to get out that opposite value of what x could be. Okay, so that's the difference there. I'll do it. Keep my color coordination here. Anytime it's negative infinity, you just have to remember to do the opposite of that value. Okay, and I can, once we do absolute value ones too, I can explain it. That's a little bit more clear, but again, these would cancel. Okay. So again, I think the easier way, though, to think of that is just to think of an example like this. So if we have an unknown being squared, it could be the negative version of that number or the positive version of that number. So if we're going to add all the negative x values, it's going to come out to be that negative version, so the opposite of whatever x is. All right, so these again cancel, but careful here, that'd make that a negative 3. Minus 2 over negative infinity and negative, well, actually that would end up being positive infinity, so 2 over large is 0. Square root of 2 plus 1 over really large, that'd be 0. So we get negative 3 over 2. And we'll graph this function. We have horizontal asymptotes here at y equals positive and negative 3 over the square root of 2. Yes?
So when you were doing the, extraction of, the x's from, below, why wouldn't you turn the 2 into a negative 2 as well? If it's the same thing going to the 3x.
This one, because it's 0.
No, the one underneath it.
Oh, this one?
Yeah, because it simplifies the same way. So that makes that a negative x.
Because I didn't actually square root x squared. Like, the x squared was in the radical, so those just undid each other. And I didn't actually have to square root the x squared.
Okay.
Does that kind of make sense? So here it actually stayed positive because that negative value squared would actually come out positive. Good question. All right, I'm going to pull up my graph real quick because I do want to show you this one. Okay. So, let's look at that function quick. Numerator, 3x minus 2 divided by, make sure you wrap your denominator in parentheses, the square root of 2x squared plus 1. Close your parenthesis. My scale's all messed up. We're doing scatter plots on our graphing calculator and calculus. Pre-calc, I mean. I'm just going to go -10 to 10. We might have to zoom out a little bit to look at the end behavior, but okay, so that's what my curve looks like. Now, horizontal asymptotes you can graph. So we could graph positive 3 over the square root of 2. Okay, that one's going to be red. So you can see how like that would be kind of like a horizontal asymptote. And we said our right end behavior approaches positive 3 root 2, so that looks like it matches in our graph. And then we could also, if we wanted to, draw in -3 root 2. And you could see, here's another good example of I did cross over that horizontal asymptote with my left end behavior still approaching that -3 square root 2 value. That's kind of where my graph is leveling off. Okay, everybody okay with how I punch that in? Kind of fun, huh? Okay. So those ones can be a little dicey. That's why I wanted to do a radical one with you, especially with the square rooting on x squared. The other ones that can be a little dicey are absolute values. So before we jump into these, you should have some room kind of at the bottom of your notes here. We're going to talk about absolute value. And you have seen this before because I actually just saw it in my Algebra 2 lesson for today. So absolute value functions are actually a shorthand for piecewise functions. So if I have just plain old parent function, the absolute value of x, okay, we know what the graph looks like. It's a V shape. So this is actually a piecewise function. Okay, you can think of you have two lines here, the blue line and the red line. So another way we can write this, and this again kind of goes back to like what we were just talking about, kind of. I could plug in a value and get out 2, or I could plug in the opposite of that value and still get out 2. So this function is this piece, all of these positive values, these positive x values. We're going to get out this piece of positive x. Think of that line like y equals x, okay, positive sloping, if our x values are positive. If we plug in negative values, now we still get out positive values, but think what the equation of this line would be. That piece of it would be negative x. All right, so you can kind of see how this piecewise function would fit this graph of my absolute value. And then that kind of goes back to like what I said before, like the square root of x squared is technically the absolute value of x. So then thinking of the absolute value of x as a piecewise, it'll be positive x or negative x, depending on what x is. Okay, if that kind of makes sense. So this is going to be how we do absolute value limits, is we kind of have to think, okay, like what piece, if I'm looking as x approaches positive infinity or x approaches negative infinity, which piece of this am I going to need to look at? And it's funny that I actually like saw this and we were talking about absolute value functions in Algebra 2 in the textbook, and it like teaches it this way. It's like, oh, it's really just a piecewise function. I was like, oh, I've never seen that before, but that's great for calculus when you get there. Have you seen that before? Absolute value written as a piecewise? No, it doesn't feel familiar? Okay, so I'll kind of show you. Here we have a limit as x approaches infinity and negative infinity of 3x plus 1 over this absolute value of x plus 2. Okay, so let's first, before we even jump to it, let's write this function as a piecewise function. So quick and easy way to do this is everything's going to be positive. So the absolute value of x is going to be positive. And I know you don't normally write positive x, but I'm going to do it just for sake of showing you. If whatever's inside of the absolute values here, which in this case is x, is positive, greater than or equal to 0. Maybe I should use different colors, but it's okay. We're going to get out a negative x, and that doesn't change the plus 2 at all, if x is less than infinity. Okay, that's that function written as a piecewise function. So that's always what I kind of do first. Like, okay, anytime I have an absolute value one, I got to look at it as a piecewise function, and then I can determine what piece I'm going to use. So here, as x approaches positive infinity, I'm going to use this piece, because obviously that's greater than or equal to 0. So you could really just think of this as the limit as x approaches positive infinity of 3x plus 1 over positive x plus 2. And then we can do our easy tactic of dividing by the largest power of x in the denominator, which is just x. So divide everything by x. Those cancel. This becomes a 1. We end up getting 3 plus 1 over infinity is just 0 over 1 plus 2 over infinity is 0. So that ends up being 3. Okay. So it's kind of similar to what we were just doing of, hey, are we going to use positive x or negative x? Depending on if we're looking at positive or negative infinity, but it's just like a little bit different algebra we're doing here. So now for negative infinity, we're going to use this piece. Negative x plus 2. And then I'm going to divide by the largest power of x, which is still just x. Again, that's the same as times a by 1 over x. So I just divide everything by x. These cancel. That's a 1. And we end up getting 3 plus 0 over negative 1 plus 0. So you end up getting negative 3 for this one. Okay. So anytime you have absolute value, rewrite it as a piecewise function, makes it a lot easier. And then just decide which piece you're going to do depending on if you're looking at the right end behavior or the left end behavior, positive infinity or negative infinity. I have like one more example we'll do of that, not today. So going back to this, it's kind of the same idea because as I mentioned, the square root of x squared, we say is the absolute value of x. It's like another way to simplify that because we don't know what x is. So really that's what we did there. We just didn't go through the process of rewriting it as a piecewise function. But similar idea there when you got to do the opposite. If you're looking at negative infinity, kind of like that, you're just using basically the other piece of it. That kind of makes sense. Okay. Last thing. This will be perfect. We're going to go back to the squeeze theorem because the squeeze theorem also works for limits at infinity. And I think we only did one squeeze theorem one together, so we'll do just a couple here. Okay, so to remind you what the squeeze theorem is, basically we try to find our function, we try to find like two values it's between, and then we do a little bit of algebra, and then we take the limit of everything, and as long as you have two values, something like this, and then if your function is always like right between them, then the limit's going to approach the same thing, so we're kind of like sandwiching it and saying like, all right, if this one's approaching 0, and this one's approaching 0, and our limit's right in between it, or our function's right in between it, its limit would also have to be approaching 0. We kind of like sandwich it, or squeeze theorem is what it's actually called, but sandwich theorem is another way of phrasing that. Okay, so you kind of have to start off by looking at a piece of your function and knowing like two values it's between. So I think the last one we did is sine. Here I'm going to start with the opposite of the cosine function, because I know very well what our cosine curve looks like. It looks like this. So the opposite, if that were reflected, it would just look like this. However, I know that this curve, no matter whether it's a regular cosine curve or it's reflected, doesn't go lower than what value? -1, and it doesn't go higher than what value? 1. So that kind of gives us a starting point of, we know this curve is always sandwiched or squeezed between -1 and 1. And I think, guys, the only ones we use the squeeze theorem are sine and cosine, so that's usually how it starts. Okay. Like almost positive that's the only time we use squeeze theorem, in this class at least. All right, so now I have to get my middle piece here to look exactly like this. Exactly like my function. So the first thing I'm going to do here is, I'm going to add 1 to everything. Over here I get 0, and then I have 1 minus cosine of x, and then I get 2 on that side. All right, now I got my numerator set, so now I can divide everything by x squared, and then I'll have my function. So 0 divided by x squared is 0. And this is okay. Sometimes it's not okay to divide by a variable because you don't know what it is, and it could be 0. But in this case, we know that x is approaching -infinity, so it's not 0. So this is okay. Sometimes people feel very uncomfortable doing that. And here I have 2 over x squared. All right, now I got my function in the middle there. That was kind of my goal. Now I can take the limit of all 3 sides of this like compound inequality we have set up here. I can take the limit as x approaches -infinity of all 3 sides and see if there's anything I can confirm after looking at this. Okay, this would obviously just be 0. This is what we're trying to find. Here I end up having 2 divided by -infinity squared. That's a positive large. So that's also 0. Okay, so now this is sandwiched in between 0. So this is what the squeeze theorem allows us to conclude. Therefore, the limit as x approaches infinity of our middle piece there, 1 minus cosine of x over x squared, would also be 0. Obviously, if it's greater than or equal to 0 and less than or equal to 0, it has to be 0. It's the only way. We could have figured this out without doing the squeeze theorem, because cosine oscillates. So it's always going to be like some value up here, 1 minus some value in between -1 and 1 over super large is going to be 0. Okay, is that going to make sense? So if we were to graph this, we would have a horizontal asymptote like 0. Let's do one more squeeze theorem. Okay, so similar to the last one, I know sine, this piece of my function, is always in between -1 and 1, so that kind of gives me a starting point. Now I'm trying to make the middle piece look like my function, so I'm going to add 5x to everything. So I end up getting 5x minus 1 is less than or equal to 5x plus sine of x, which is less than or equal to 5x plus 1. Then I can divide everything by x. Again, this is okay because we're looking as x approaches positive infinity, so you know x can't be 0. And I get 2 here. 5x minus 1 over x is less than or equal to 5x plus sine of x over x. So that's what we wanted. Less than or equal to 5x plus 1 over x. All right, now instead of writing this back out, I'm just going to take the limit of everything. Oops, I put 0 there. Okay. Here, we can just divide everything by the largest power in my denominator, which is just x. You want to write up here, we just times the top and bottom by 1 over x. Middle, we just copy down. That's what we're trying to find. Here, same thing. Divide everything by the largest power of x in the denominator, which is just x. Okay. So here, these cancel. We have 1. I'd have 5 minus 1 over something really big is 0, so I'm just going to cross it off. 5 minus 0 over 1, which is just 5. Okay, I'm not going to rewrite this one. Same thing here. X's cancel. Here I have 1. X is going to be going off to 0. So I'm having 5 over 1. So now this is sandwiched between 5. So we can conclude that the limit as x approaches infinity of that middle piece would also be what, guys? 5. Which means it has a horizontal asymptote where?
5.
Y equals 5. Yep, good. Okay, really quick. Do you recognize this trig identity? Sine squared of x plus cosine squared of x is the same as what? 1. Yep. So limit as x approaches infinity of 1 would just be 1. Horizontal asymptote at y equals 1. Some people see that and they get really intimidated. They're like, oh my gosh, squeeze theorem, what do I do here? Trig identity. Okay.